Good morning, everyone. Now we're going to start chapter 5. Chapter 5 is going to approach our statistic abilities from a different aspect. Up until now, we've been using frequencies to determine the graph, the histograms, the mean, median, modes. Now we're going to look at what are called probability distributions instead of frequency distributions. We're going to analyze these mean, median, mode, the statistics based on the specific probabilities of each event occurring. So we're going to use a few new terms here. We're going to define random variable. We're going to describe or define a probability distribution. We're going to look at once we have a probability distribution, we can now draw a probability histogram. We're going to calculate the mean, standard deviation, and variance based on these probability distributions. Again, because we have a histogram, we can look at the mode, and we can't really find the median here because now we're looking at probabilities, but we can see which one occurs the most. So you can calculate mean, standard deviation, and variance of a probability distribution. And then lastly, we're going to determine whether our outcomes are significant. They could be significantly high or significantly low. So, we talked about that last chapter. So let's begin. The basic concepts of a probability distribution. Again, all the words. Let's define random variable. Random variable is a variable or variables. We call it X with a single value that is determined by chance for each outcome. So it's determined by chance. It's random. So the probability distribution is a distribution or It's a distribution that describes, it's a description that gives the probability of each value of the random variable in the form of a table found by a formula or graph. All right, so now we have two types of random variables. We have two types. Discrete and continuous. Remember earlier in this course, we talked about discrete and continuous variables. Let's define those. A discrete random variable is a variable whose values are that of a finite or countable data set or a sample space. So the values that are given this are finite and countable. So, all right, if you had 10 people choose from, those are countable. Each person is assigned one number and they're countable. Okay, now it says finite. If you have an infinite number or infinite many values that can be counted, or the first, second, third, and so on and so forth, then that infinite one is discrete. So basically it's countable. That's really what you look for. If you can associate the number of variables or each variable with a number, then it's countable. As opposed to continuous random variable. A variable that has infinitely many values. And the collection of those values is not countable. Basically, we're looking at decimals, because between 0 and 1, there are an infinite number of numbers. So chapter 5 will deal with this stuff, and the rest will deal with continuous. We first have to look at continuity of numbers and how to connect, how they can relate to each other. The requirements of a probability distribution. All right, so in order to be, it has to follow these 3 basic rules. Three requirements. First requirement. There is a numerical, not categorical, random variable x, and its number values are associated with their corresponding probabilities. Okay, the first one has to be numerical, which means you can add, subtract, multiply, divide. Cannot be categorical. Red, blue, tall, short, because we can't do calculations with those. So we can't find, you can't find the probability of red, but you can quantify it. You said how many of this category are there. That has to be, our numbers have to be categorical. I mean, numerical, not categorical. It's condition 2. The summation of all probabilities has to equal 1. Or very, very close to 1. In other words, 0.99999 or 1.0001. It could be larger and smaller, but it's got to be very, 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 very close to it. But all the probabilities have to add together to be 1. So the first one says you have to have probabilities. The sum of those probabilities has to equal 1. And each probability must be between 0 and 1. So the probabilities of each random variable discrete random variable, where X is a discrete random variable, each one of those probabilities has to be between 0 and 1. Okay, so let's look at our first example. Let's look at the coin toss. Let's consider tossing 2 coins with the following random variable. X is the number of heads when 2 coins are tossed. That's what we're looking for. So what can happen? So here's our X. These are, but what values go in here? Let's look at our possible outcomes. Remember, we have 2 coins being tossed and we're looking for heads. So if you have tossed 2 coins, the first coin, second coin, we can have tail, tail. So there's no outcomes possible. You can have the first one heads, the second one's tail, or the first one's tail, the second one's heads. So you have the possibility of 1 head. There's number of heads. So you have no heads, you have only 1 head, or you can have both flips gives us heads. So those are the outcomes, the number of outcomes of heads being tossed. Right, so now we can look at the probability of these. Well, let's look at the frequency first, because we need the frequency to find the probabilities. This one happens once, this one occurs twice, and this one occurs once. So remember, n equals the summation of all your frequencies, which is 4. Now we look at the probability of each event, probability of each x. It's the frequency over the n. So for 0, no heads, it's 1 over 4, which is 0.25. Or we can have, with 1, there are 2 possibilities, 2 over 4, which is the same thing as 1/2, which is 0.5. 0, because went to those places. And likewise, the last one only happens once, so it's 1 over 4, which is 0.25. Let's look at this. Do they match our 3 conditions? Are they numerical? Yeah, we could take these, we can quantify them. So they're numerical, check. If we add up all these, the summation of all your probabilities, 0.25, 0.25 is 0.5, 0.5 plus 0.5 is 1.0. Check, that's the second condition. And the third condition, are each of these probabilities between 0 and 1? Yes. So it is a normal distribution, not normal, but a probability distribution. All right. So that's how we do the first one. Another notation. A notation for 0 plus. So in other words, if our probability, value is very small, but still greater than 0, we say it is 0 plus. That means it's on the bigger side of 0, but we won't write those small decimals like 0.000091. That's 0 plus. All right, let's look at the probability. Since we can make a distribution, we have a chart made out of it, we can now have a probability histogram. Graph of a probability distribution. Remember, a histogram is made up with bars. That's a histogram. So in our case, in this probability histogram, the vertical axis is our probability. And our horizontal axis deals with the actual results. So for our example, our outcomes were 0, 1, and 2. Outcomes, or number of heads. And here's our probability. It's 0.25 or 25%. This is 0.5, 0.75, and 1.0. The first one, at 0, we had 25%. So our value goes in the middle of that rectangle. 1, we had 2 of those, so that was 50. So they share a side. And that, again, the x-axis 1 goes in the middle of that box. And the number of 2 outcomes that we had is only one of those. So what you could do is you could put 25%, 50%, 25%, because this will help you count to make sure that they all equal 100% when everything is said and done. Okay, then. So that is our histogram. It's not much different than the other one. Let's look at our probability formula. The formula we'll be using is the probability of our event is equal to 1 over 2 times 2 minus x factorial times x factorial. Where x is our possible outcomes, which is 0, 1, and 2. or 2. No, it can't be all the same times. So let's look at this. Well, okay, now that symbol is called a factorial. A factorial simply means multiply each term from 1 to n. So if I had 3 factorial, I multiply each term from 1 to n. So that's my n. So it's 1 times 2 times 3, which is 6. 5 factorial starts at 1 and goes all the way to 5. 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. So that's what a factorial is. So let's look at what would happen if we had 0. Because this is the number of outcomes. So we have 1 over 2, 2 minus 0 factorial times 0 factorial. Note, 1 factorial is just 1. If you have 0 factorial, that also equals 1. Because the lowest you can go is 1. There are no zeros in factorials. It just, if you have a 0, it's 1. All right, so we get 2. 2 minus 0 is 2 factorial. 0 factorial is 1. 2 factorial is 2 times 1 times 1, which is 2 times 1 is 2. 2 times 2 is 4. 1 over 4 is 0.25. So the probability of 0 is 0.25, which is what we got earlier. That's what we got earlier. We do the same thing with 1 and 2. Let's look at another example here. Job interview mistakes. Hiring managers were asked to identify the biggest mistakes that job applicants make during an interview. The table represents their responses. Does a table describe a probability distribution? Remember, probability distributions has 3 conditions. It is numerical. The summation of all the probabilities has to equal 1. And each probability has to be between 0 and 1. So these are not numerical. They're categorical. Inappropriate attire, being late. So they're not numerical. That fails. Are each of the probabilities between 0 and 1? Check, 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 check. So that one works. Is the summation equal to 1? No. So this table violates 2 out of 3, so it's not a probability distribution. Let's look at these formulas now. parameters of a probability distribution. First, we're looking at probability distributions describes populations not samples. So that's first important because we're looking at the entire population of everything that's happening. That's what we're looking at. So probability distributions describe populations and not samples. So what does that mean? We have to use Greek letters for the mean, standard deviation, and variance. So that's the thing. And also, since we're describing populations, a population we use, or we find parameters and not statistics. Since we're describing a population and not a sample, we use parameters, not statistics. So let's look at our three formulas that we're going to deal with. The mean of a probability distribution, that's the mu. The formula is this. It's summation of all your outcomes times their probabilities. Remember, when we use the frequency chart to find the mean of the frequency chart, we took the value itself times the frequency and divided by how many we have. And that's exactly what this is all about. Because remember, probability is frequency over n. So these are all taking that in consideration already. So we have now standard deviation of a probability distribution the symbol we use there is rho. This is mu. This is rho. It has like like a Charlie Brown head. So the standard deviation is simply the square root of the summation of x squared times the probability, all those minus the mean squared. The variance or standard variation of a probability distribution, which is rho squared. We have two different ones here. Rho squared can equal x squared times p of x, which is what we have in here, minus mu squared. Because remember, the deviation is simply the square root of the variance. So if we square root this one, we get that. This is the one we most often use. Or there's another one we can use. Rho squared equals summation of x minus mu squared times p of x. And this one's difficult because we have to first find the mu. Then we have to take each one separately, subtract them. Then whatever we get the difference there, we have to square them. Once we find that, we have to multiply it to the probability, and we have to add them all up. So that's a lot of extra work. In this one, we take the values, square them right off the bat, and multiply their probability, add them up, and subtract by the mean squared. All right, so those are the formulas we'll be using. Oh, well, the round off rule. For mu, rho squared, and rho. The mean variance deviation. So it's round the same as always, round the results to one more decimal than the number of decimal places of the variable x. Note, if x is an integer, use one decimal place for our solutions. But there are sometimes where we have exceptions to that round off rule. All right, so. But for most part, that's it. Expected value, because remember, we're trying to we're trying to get our answer closest to the population and talk about that. So the mean of a discrete random variable x is what we call the theoretical mean. For infinitely many trials. So the mean of a discrete random variable x is the theoretical mean outcome for the infinite many trials. Remember, we're dealing with populations here. That's what for random discrete random variables, for discrete probabilities, we have populations. So that's why we're using infinitely many trials to analyze this. So the mean is the expected value meaning the average value we would expect to get if the trials continued indefinitely. So the mean is the expected value. It's a theoretical mean. Okay, the theoretical mean is what we theorize this is what would happen if we kept on rolling infinite number of times. So that mean, theoretical mean, is the expected value. Let's look at the notation for it. The expected value we'll call it E. So E is equal to, since it's the mean, it's the average of all the entire population, and E is also equal to the summation of your x's times your probabilities. That's your formula for it. But remember, that's the formula for the mean. And because of this, if your x's are integers, your answer may not be integers because the probabilities may be decimals. So the expected value is the mu. The mu is the mean of the population. And the formula for that is x times the probability of x, add them all up. All right, let's take an example here. The table below describes the probability distribution and number of heads, 2 coins. Okay, so we know that we can get no heads, 1 head, or 2 heads. So the outcomes could be tails, tails, heads, tails, tails, heads, or heads, heads. I'm sorry, oops, I got this backwards. Heads, yeah, I'm sorry, I was right. Because it happens, there are 2 heads there, only 1 head there, sorry. So this happens once, twice, once. If we add up those, we get 4. So these are your n. Remember, the probability is the frequency over n. So 1 over 4, which is 0.25, 2 over 4, which is 0.50, 1 over 4 is 2.5. The summation of all your probabilities has to equal 1, and it does. Now, what do we, let's look at these now. We have this filter created. Let's calculate the mean. The mean, it's the mu. It's x times p of x. So we have x times p of x. So 0 times 0.25 is 0. 1 times 0.5 is 0.5. 2 times 0.25 is 0.25. And that one, the mean is not correct. But that equals 1. Oh, let me look at the data correctly. The summation is 4. Probabilities x times p of x, so it's 0 times 0 is 0. 1 times 0.5 is 0.5. So this one added up is 1.0. Okay, that's it. It is what it is. So the summation of x and p of x okay, now the variance is summation of x minus mu squared times p of x. So we have to have x minus mu and mu is 1.0. So 0 minus 1 equals -1. 1 minus 1 equals 0. 2 minus 1 equals 1. So that's the in part and side part. We now have to square that to get rid of the negatives. So -1 squared is 1, 0, 1. Now we have to multiply times p of x. So 1, so we have x times, or x minus mu squared times p of x. 1 times 0.25 is 0.25. 0 times 0.5 is 0. 0.25. Add up all those. We get 0.50. So the variation is 0.50. So the deviation is simply the square root of the variance. So it's the square root of 0.50, which is approximately 0.7. I just thought that s equals 1, that's 100%, but no, we're looking at the part of a calculation, so it doesn't matter. Great. So the mean, let's see what this means. This describes stuff. Remember, we're looking at 2 coins being tossed. The average of getting 2 heads is 1.0. The variance is 0.05 heads squared. So we have to have, and then the last one is also our units. Let's look at significant values. Making sense of the results. We have 2 different ways for finding whether a value of a random variable x is significantly high or low. And identify significant results with the rule of thumb approach. Remember we did that last chapter. The rule of thumb is how we interpret our outcomes. So remember, the rule of thumb says that any value within 2 standard deviations from the mean are not significant. If a value is higher than the mean plus 2 standard deviations, then it is significantly high. If a value x is below 2 standard deviations of the mean, then it is significantly low. So anything in the middle is nothing. It's good. And the chart that the graph that they used earlier in the last chapter. So it's the mean minus 2 standard deviations. The mean plus 2 standard deviation. And here's the mean. If it's here, it's not significant. So here it's significantly high. And here it's significantly low. This is just a guideline, so don't take it as a law. So that's the rule of thumb. Once you find the mean, find the standard deviation, add 2 standard deviations, subtract 2 standard deviations, and those are your cutoff points. Any values that are above those or below those are significant. All right. In example 3, we found the tossing coins, the mean number of heads is mu equals 1.0, and the standard deviation was 0.7. Use those results and the rule of thumb to determine the range rule of thumb, that's what it's called, whether 2 heads is significantly high number of heads. So we first create, so our mean is 1.0. 2 standard deviations is 0.7 times 2, which is 1.4. So the mu plus 2 standard deviations, which is 1 plus 1.4, that equals 2.4. And then mu minus 2 standard deviations. So 1 minus, it makes it negative 1.4, so we stop at 0. Because you can't have a value of negative here. So what it's saying here is determine whether 2 heads is significantly, so the probability of 2 heads was 0.25. So what do we get there? 0.25. So no, it is not significant. All right, so that's how we're looking at. Because anything higher than that significant, anything lower than negative 0.4 is significant low. Since they're looking at user results and the rule of thumb, range rule of thumb to determine whether 2 heads is significantly high number of heads. And we did that. We did the probability of 2 as 0.25, and so it's not. All right. Let's see here. Rare value. Let's look at another example. Significant results with probabilities. Our 252 heads in 460 coin tosses a significant high number of heads. What does the result suggest about the chapter problem? The chapter problem was about the football. We had to talk about football games, that 460 teams winning a coin toss for overtime. 252 of those teams won the overtime game. So is it significant? All right, so let's look at this. The first one. 252 heads in 460 coin tosses. So if it was by chance, we look at around 230. So that's just a little bit above what's expected. But is it significantly higher than expected? No, we're not given the exact probability just yet. Okay, so yeah, right now we won't be able to do this. I don't know why I put this in there. Oh well. Are 252 and 460. That's above 50%, but not significantly high. Yeah, which we have to create the form chart. I forgot the chart. I'm sorry. Oh yeah, let's just void this one out. I forgot the rest of that chart information on there. Oh well. Let's look at expected value and the rationale for the formulas. Plural. Remember, expected value is since we're dealing in probably distributions here, we're looking at populations. So the expected value is the mean. And the formula for the mean was X times the probability of X. So now why do we do that is by definition, the expected value is what do we expect to happen since we know the information of the population. So this rationale of this is, if you look at this as probability is frequency over n. So what this formula looks like is X times frequency over n. And this is exactly what we used to find the average of a frequency histogram of a sample. So we just now use the very large n to find this information. All right, let's look at this one. Be a better. I like that. Be a better. You know, this is somebody who bets. Be a better person that bets. You have $5 to place on a bet in the Golden Nugget, the casino in Las Vegas. Golden Nugget's one of the oldest ones on there. It's on the main old part of the town. You have narrowed your chances to one of two bets. The roulette, bet on number 7 in roulette, or craps, bet on the pass line in the dice game of craps. The pass line on the come out is you're hoping for the person to roll a 7 or 11 on the first roll. Reason that, because 7 is the most frequently occurring number on with you have 2 dice being tossed. So if they roll a 7 on the first one, craps, then you win money. But if they don't roll a 7, anything else above that becomes what's called a point. Except, of course, there's always 2. That's a bust. But anyway, it's snake eyes. So after anything above that becomes a point, which keeps on rolling until he gets it. So if you bet $5 on number 7, the probability of losing $5 is 37. Because in roulette, that's the wheel. That's the roulette. There are half the numbers are red, half the numbers are black, and it has 2 green, a 0 and a 00. So you have this 36, 38. So it's, I believe it's 18 of each. That makes 38, yeah. So the probability of losing is 37 out of 38. Okay, now they're only playing with only one green. They have 2 of those. So you have 38 possibilities to play these. 36 plus 2 is 38. You have a 0 and a 0. So losing your $5 bet, you have all of those except 1. So you have 37 out of 38 to lose. You only have, this is to lose, and to win, you only have 1 out of 38. So this is how this looks. The event is to lose or to win. There's only 2 possibilities. If you lose your $5. If you win, you get $175. It's actually 180 because if you add those together, that equals your 180. That's how much you would get back from the dealer. But 5 of those is yours to begin with. The probability of losing is 37 over 38, 1 over 38. And if you add up all those, you get 38 over 8, which is 1. So the probability (5 times 37 over 38) that's negative. It's negative 4.868. Since that's dollars, it's dollars. This one, 175 divided by 38. They're both positives. It's dollars, which is $4.6052. Now, if you add these two, 4.6 minus 4.8, it's going to give you a 0.26 about. So you basically lose 25 cents or 26 cents each time. Remember, if you add up all these, this is your average. So on the average, you're going to lose 26 cents every time you play. Now, if you bet, this is now for the craps table. If you bet $5 on the pass line of a craps game, the probability of losing, so this is again, the event is to lose or to win. If you lose your $5. In craps, if you win, you only win $5 on the pass line. So the odds of winning 244 over 495. So that means if this is 244 over 495, 495 minus 244 is 251, because both of these have to equal 495 over 495 has to equal 1.0. So now we take this column times this column. So -5 times that would equal a negative 2.5353 forever. And this one, positive times this, gives you 2.4646 forever. So this one's negative. So if you add those two together, what you'll end up with is a negative 0.07 cents. So you'll lose about 7 cents each roll. I mean, so that's why if you go and you just bet the pass line or don't pass line, you'll be out 7 cents here each time. This one you'll be out. This one you'll be out a quarter. All right, so that does it for that section. Good luck. I'll send you out the homework assignment as soon as I finish these.